Good morning, students. Today we are going to learn manufacturing of ceramic matrix composites and particularly self-lubricating CMCs and carbon fiber reinforced carbon matrix composites. So both are carbon. I am Nilanjan Das Chakladar, Assistant Professor of Mechanical Engineering Department, IIT Kharagpur. So coming to self-lubricating CMCs, strong ionic or covalent bonds between the atoms of ceramic materials determine their strength, hardness, high melting point, modulus of elasticity, temperature and chemical stability. So there is a direct relation between the strength of the covalent bonds and the material properties. Coefficient of friction is lower in high surface finish ceramics with fine grain structure. Continuous supply of a solid lubricant to the ceramic surface may be provided by the ceramic material itself if it is a composite material, with the ceramic matrix containing dispersed particles of the lubricant, which is called as the self-lubrication. So these are some of the examples of solid lubricants like graphite, boron nitride, sulfides, selenites, oxides, and soft metals. Coming to carbon-carbon composites. Now we are moving on to the most advanced ceramic matrix composites, where the matrix is carbon and the reinforcing phase is carbon fiber or carbon particles or carbon chopped fibers, carbon fillers, but both are carbon. So what we see here on the left, obviously it's a aerospace application, the brake discs within which there are unidirectional carbon fiber reinforced on carbon matrix composite. Okay. On the right hand side, what we see is whatever we have studied so far, if we try to plot the overlap, the domain of these different material composites in a plot, in a two-dimensional plot with y-axis is the range of temperatures and in the x-axis we have the tensile strengths. Okay, so what do we see? CFRP, you see it is leading on this edge. It's a carbon fiber reinforced polymer. However, the temperature is lower. On the other extremity, we see SiC, that is the silicon carbide, the carbon-carbon matrix, and the advanced carbon-carbon matrix at a very high temperature with moderate strengths. Okay. In the middle, what we see all the metal matrix composites are lying in the middle. So this is a classic example where whatever we have studied so far with polymer matrix composites, metal matrix composites and ceramic matrix composites, we could see that from one extremity to other extremity, the ceramic composites are winning over the polymeric composites. However, that does not mean that polymer composites are lagging behind. So researches are still going on in that direction. So coming to the fabrication of carbon-carbon composites. Structure, carbon-carbon composites may be manufactured with different orientation of the reinforcing phase. The UD structures, bidirectional, multidirectional, we'll see after a couple of slides that there are plenty of variants of carbon-carbon composites, particularly from the orientation of the reinforcing phase. Okay. Now, what are the two different methods, fabrication methods for carbon-carbon composites? One is LPI. We have already studied earlier in the ceramic composites video lecture. The liquid phase infiltration. Another is the chemical vapor deposition. So the carbon fiber preform structure, it can come through two routes. In one route, it's a liquid impregnation of thermosetting resin, pitch. Then there is carbonization from 500 to 1000 degrees Celsius. Try to note here, when we talked about manufacturing of carbon fiber, there was also carbonization phase. There was carbonization, there was graphitization, and gradually we could draw the filaments. Now this cycle is repeated about 1.5 times. Okay, as we know that pyrolysis, the infiltration cycles, they have to be repeated for better densification. On the other hand, we have chemical vapor decomposition of the hydrocarbon gas at a relatively similar temperature, which is 1000 to 1200 degrees Celsius, but it is again repeated 1 to 3 times. Finally, there is a heat treatment at a further higher temperature and we get the carbon-carbon composites. Okay. So what are the steps in the liquid phase infiltration? Preparation of carbon graphite preform of desired shape and size. Infiltration of the preform with a liquid precursor. In this case, since we are talking about carbon, it has to be petroleum pitch or phenolic resin or coal tar. Pyrolysis or carbonization, that's the third step. Chemical decomposition by heat in absence of oxygen, very important. You have carbon, you have oxygen, you get carbon dioxide, carbon monoxide, immediately it oxidizes. We do not want it to happen. What we want the decomposition, the chemical decomposition by heat, but in absence of oxygen, of the polymer precursor. What is the polymer precursor here? The petroleum pitch, phenolic resin, all this. Next is the infiltration step. Pyrolysis cycle is repeated several times until the desired density is achieved. So this thing you have now heard multiple times, 100 times for each fabrication method of ceramic matrix composites. Improve the density, increase the density. We have to enhance the density. The densification is very important. Graphitization heat treatment. So carbonization is done. Now graphitization comes at a higher temperature compared to carbonization. At this stage, amorphous carbon is transformed into crystalline graphite. The treatment temperature may vary within range, the higher range 1500 to 3000, typically around 2500. And because of this graphitization, the tensile modulus as well as the tensile strength of the carbon-carbon composite increases. Next, with CVD fabrication, chemical vapor deposition, preparation of carbon or graphite preform, this step remains the same. Densification is required, but here you are repeating the CVD cycle, and graphitization of heat treatment. We can see two brake discs have been shown made of carbon-carbon composites. Now in this particular slide, what we see is along the row there is the axis. How we can define the orientation of the reinforcements axially, and along the column what we see is the dimension. So while naming it, what is 1D, what is 2D, what is 2.5D, what is 3D, those things. So 1D, we could see only roving or yarn is there, which is in one axis, so monoaxial. 2D, that could be chopped in random directions. It could be pre-impregnated sheet, but in 2D, in a sense, it has one in this direction. It is monoaxial, but it is in a two-dimensional geometry or two-dimensional form, 2D form, like a tape. In biaxial, we could clearly see two axes. In two axes, we get two different tensile modulus, tensile strength. This is a two-dimensional one, which is a plane weave. Classical example, we have also studied. Triaxial, now we incorporate along the z-axis. Multi-axial, we are incorporating in different planes. Okay, so basically triaxial is a type of multi-axial. Coming to 3D, 3 dimensions. It could be linear like a strand mat, 3D braid, multiply weave, triaxial 3D weave, the same triaxial weave in different layers, multi-axial 3D weave, 3D plane element, laminate type, H or I beam, and honeycomb type. That's a triaxial. Now there are further other different variants of the structural design, which is more toward different types of woven designs. Okay, different types of weaves: biaxial, high modulus, multi-layer, triaxial, tubular braid, etc. In addition, there could be biaxial bondage, flat braid, then 3-directional array, 5-directional array. There are so many variants. The more the variants, more we are keeping in mind the structural integrity of the composites. Now coming to the properties, excellent thermal shock resistance, low coefficient of thermal expansion. We require definitely this for space applications. High modulus of elasticity, high thermal conductivity, low density, high strength, low coefficient of friction, excellent heat resistance in non-oxidizing atmosphere, high abrasion resistance, electrical conductivity and non-brittle fracture. Okay. The disadvantage is low oxidation resistance. So that one has to work on. Carbon reacts with oxygen at a temperature of 482 degrees Celsius. See, it's a very low temperature. Compared to the performance of the carbon, this temperature is quite low. Methods for oxidation protection of carbon-carbon composites. That means now you have to protect the surface of the carbon-carbon composite so that it does not come in contact with come in contact in an oxidizing environment, or basically does not come in contact with oxygen. So protection coatings, multi-layer ceramic coatings of carbide nitride on top of the surface that can be deposited by CVD, PVD or plasma spray. Impregnation of oxidation inhibitors, inorganic salts, borates, phosphates, and replacement of matrix from carbon to silicon carbide. That means carbon silicon carbide composites possess excellent oxidation resistance. So this is a catch. Okay. Application: high performance braking, refractory material, hot press dyes, heating elements, turbojet engines or rocket nozzles. Thank you.